in terms of subnetting. So we will have if we have a slash 32, then we'll have almost 65,000 slash 48 subnets. So here the same picture in terms of subnetting. And how do we subnet IPv4 and IPv6? Because we need the address of IPv4 to not to spare while allocating to our customer. We don't want to waste our IPv4 addresses, but in IPv6 the wastage is not our prime concern. The prime concern how we can manage it, how can we actually aggregate it eventually. So in slash 64 of IPv6 address, there is a huge number of hosts. So host is not actually our prime concern. So if we subnet an IPv6 prefix, there are lots of ways. Some of the typical subnetting is like /16, /32, /48. It's based on the hex digits that we have in each segment of an IPv6 address. So if we take a typical host, it will look like this. We will have a /64 host prefix, host part, and then the subnetting prefix will have a /64. So this is an example of a /32 prefix that we can get from the RIRs. So if we have a /32 prefix, then we also try to provide /64 addresses to the clients or sites, then we are left with only 32 bits that we will twist for subnetting and planning of IPv6 allocations. So this is another example with the /48. Then we have only 16-bit to subnetting the prefixes. There are some other examples like /52, /56, /60. So how we can do these subnettings? We need to consider the nibble boundaries. The nibble boundaries is actually the 4 hex digits. So here is an example like we have this 1, 2, 3. So 1, 2, 3, 4 is just a nibble bit boundaries that we have. So in this 4 hex digit, there are actually 16 binary bits, and these binary bits are like this. So if we try to, why actually we need to know the nibble boundaries? Because during subnetting, the IPv6 representable format is with hex bits, but actually subnetting occurs in binary bits, right? So each hex bit has 4 binary bits inside one hex digit. So if we consider one of these hex bits, hex digits, then actually we have to consider 4 set of binary bits. So if what will happen if we don't consider the nibble boundaries? It's okay, it's not technically wrong, but it's actually much difficult to manage and maintain the subnets. Like here's an example: if your subnet is not a slash something that is not a multiple of 4, then what will happen actually? So should we receive it? Sorry, so I need a break. So it's good actually. So if we have a subnet that is a multiple of 4, okay. So then we can consider, like here is an example of a IPv6 prefix that has been subnetted at /48. So this one is a multiple of 4. So we have considered each hex digit to subnet that. Ultimately, we have considered 4 binary bits. So then here these bits are fixed and these are variables. So we can take any of the hex bits, hex digits to subnet our IPv6 prefix. But what will happen if we don't consider the multiple of 4 bits? So here is an example, bad example in fact. So this slash 50, this subnet, the slash 50 is not a multiple of 4, then what will happen is we are actually subnetting something in between this 8, okay? This 8 is actually a hex bit having 4 binary bits inside. And we are taking 2 of them and we are leaving behind two of them. So we have to choose actually some of the selected prefixes like this. So this one is the binary format of 8. So this is the binary format of 8, and we are taking 50, that is 48, then another 2 bits. So these 2 bits is here. So this one is actually like network portion, so we cannot vary this one. We have options to change these, like 4 options here. So we are actually subnetting only 4, where we should subnet each bit with 16, like 2 to the power 4. Okay? But we have option only to get 8, 9, A or B. So it's better to consider the nibble boundaries while subnetting. So these are some subnet examples that have been considered with the nibble boundaries. These are not the examples that we are talking about. Like slash 50 is not. So with slash 50, we have only 8, 9, A, and B subnets. So these are the same examples. These are like easy examples, easy subnets, and these are like complicated ranges. So based on this discussion, like the key point is we should focus on the 16 bits and the 4 nibble boundaries. So here my prefix is slash 48, my host is slash 64. So I have only I have 16 bits or 4 hex digits to consider for subnets. So while subnetting, the nibble boundaries should be considered for easier planning. So the next plan is how I should work with the for a slash 48, how I should plan for the subnets of IPv6. So we can plan using regions or sites. Then we can think of locations. We can think of user types or business units, and applications, maybe data, voice, or server farms, videos, like this. Or we can consider the combinations of each of them. And actually, planning for IPv6 planning, how we will consider submitting the prefixes is based on our requirement. There is no single answer which can be applicable for every organization. So based on our requirement, we have to plan what we need. So during planning, we may consider like do we need to optimize our security policies? Then if we want this, then we may have several subnets for each and every services. Then we may consider like whether we want to optimize our routing tables. So we have to aggregate the prefixes. Finally, we have our routing table less populated, and then we may have some high quality types of objects. Like we may have 2 locations, but we may have 20 applications running in these locations. So for an example, we are taking a slash 32 prefix for an ISP, and maybe the parent block is like this slash 32, and then we can first we can take the first hex digit to allocate in each region. Like for Dhaka, we can choose 1, for Chittagong 2, for Pune. Like like this. So first neighbor boundaries we'll allocating for the divisions or regions. Then the second one maybe for the distribution box, like the first one means it's Dhaka, and second neighbor boundary bit hex digit we are considering for the distribution box. Like in Dhaka, we may have several distribution box like UGC, BUET, NSU, NU. So we'll actually allocating each hex bits for hex digit for distribution box in a particular region. Then for the third hex digit, we may consider it as edge router or maybe access port or and the last and user end problem. For Dhaka, in Dhaka region, there could be a distribution for BUET, and in BUET, there could be a customer like Dhaka University or something like that, or BSMMU or JNU. So for the third bit, we are considering the access or edge routers to allocate the IPv6 frequencies. So for a yeah, sorry, it was a mistake. Like it should be slash. Okay, no, it's okay. So for customers, but when we reach the edge routers in our network, then we have to allocate prefixes to our customers. So we should consider like /48 because it's routable in routing table. So based on the requirement of the customers, we can put some policies over there. So when we have already got 3 bits, like one for Dhaka, then for BUET, then for let's say BSMMU, and then we are leaving with another hex digit. So we can assign it like first one for our infrastructure cell, second one for customer 1, customer 2, customer 3, like this. So here is an example of this sort of applications of IPv6 addresses. Like the 5, 6, 7, 8 here. This one is first one we are putting it for buildings. Like with this one hex digit, we will get 16 combinations of prefixes. So we can allocate building wise. Then we can allocate the second 2 bits. Second one hex digit for the user types, or and then for the next 2 digits for services. Okay, so if I have many locations, then we can, for locations we can allocate 2 bits. Then we will get 256 combinations, 256 combinations. And then if we consider like I have several business groups, and then we can do the subnetting, considering the business group first, like corporate, finance, marketing, engineering. These business groups have been allocated with the addresses which subnetted using the first hex digits. Then we can consider the, for example, engineering section. They could have services like data, voice, video, wireless. So the second hex digit can be considered for the services. For example, the third hex digit can be considered for regions. Like engineering sections have data services in eastern regions, or we can have the fourth hex digit for our sites. So like this, we can do our own planning. Then, if we don't consider the business groups first, we can consider the services first. It's just our own plan, what we want. So like this, we can have some voice service in southern region, in marketing department, in site 1. Okay. In this way, we can move ahead with the plan. So how we will plan with the IP, how we will consider the IPv6 address to use in our network, and we need a good plan. So what can be the options? Like we can have multiple /48 per pop because we have to allocate it to our customers. Then we have to separate our infrastructure block from our customer block just for security. And each site or each subnet will have a /64 address space. Auto-configuration can be done there for less hassle. So then the router, in routers, we should assign each edge box with the /56 or /52 as a bigger spaces so that we can scale in future. So per interface there will be a /64 assignment, and then we can scale for more infrastructure interfaces. And VLAN numbers, I think IPv4 is already. We are considering IPv4 already done, so VLAN plan is already done there. So there is no need to change the VLAN plan. So like this for the loopbacks, we will allocate /64, but we will use it /128. And point-to-point connections, we reserve a /64 for each point-to-point connection, but while using, we can use a /126 or /127. 127 is good. For future growth, like there could be some options. We can assign the numerical prefixes like incremented by 1, like 0, 1, 2, 3, like this. Or you can have some sparse allocation. Currently, you may use the one subnet, and you can have some spare prefixes with consecutive prefixes for that particular site, and then allocate after that for second site. And there could be another option like worst option, random allocation, and you have to pay some paying for that, so better avoid it. So how you will calculate your requirement? First, you can take a, for example, you can take a location for your first hex digit. Then you will have to calculate how much locations you may have. For example, if you have 22 locations, then you have to you cannot allocate one hex digit because it will create only 16 subnets. But you need 22, so you can assign 2 hex digits for that. So then you can go ahead with the same plan for the second digits or third digits. For servers, you may use like the port numbers. For DNS servers, you may use the 53 address as the host address for the server, DNS server, like this. For customer assignments, go for /48 and update your ethnic database with information. As customers may not have the proper information to use the IPv6 or to how to plan the IPv6 addresses, so give them information so they can have a better plan. For management, most of us, I mean myself too, I use the Excel documents initially, but I think it's not scalable, and in future it will be a big Excel document. So try to use the IP address management softwares, or there will be some free and commercial softwares. You can use that. So while working in bdN, these are some of the information that I gathered from my working here, and also some documents from Internet Society's Gilbert 360 program. Then while working in bdN, there are some something I have learned, like we have 2402 F500. This /32 is allocated from ethnic to us, and then we have 32 bits to subnet our IPv6 address. So with that, we go for first we took the initial /16, I mean 16 bits per subnet. So what we did is we actually planned it with first hex digit as regions, like this, second one for UTC dual individual ports, and then the clients. So we have many clients, that's why we keep 2 hex digits, this 2 digits for our clients. Then at the edge router, so what we did is, here this Dhaka region, we have dual as distribution node, we have client like Dhaka University. So here is the example of our plan. It's like Dhaka we have assigned /36. Then for each district dual national, these are some distribution costs. From that, we have some clients like bdN, Agricultural University, JU, BTX, whatever it is. So we use 1 as Dhaka, 0 as EDC, 0 for bdN, and 0 for the services account. Then we keep another /48 spare. So this is the sparse allocation. We keep another 1 spare, and then we use 2 for customer, then we keep another spare for clients. So what was the challenge? Actually, bdN was new and it don't have any network before. So we have some benefits, like we can do some trial and error, and we can try some options. And we have some, we don't have any equipment that don't support IPv6. That was another benefit, and we don't actually deal with the customer IPv6 equipment. So this is some problem, the dongles and stuff they don't support IPv6. So we actually don't deal with that, and we don't have any DHCP-V6 or NAT64 issues. But challenge was like we don't have expertise on IPv6. Then we have to do lots of trials and errors for that. We have actually initial plan was not good. Then we have to do some works to make it a better plan. And we have to implement. We actually need to implement BCP for dual stack from day one. This is a case study for one of our customers, Jahangirnagar University. We have some IPv6 plan for them. So we assigned them /48. So these 4 digits came from the initial plan, and they got /48. So they have to do their work based on that. So we did their plan by ourselves. We considered these 4 legal boundary bits, and then we suggest them to consider the first one as service, like data, voice, Wi-Fi, etc. The second 2 bits for departments, because they have lots of departments, so we need to consider the 2 bits. And then the last one we considered for the sites, like physics department could have 2-3 buildings. So based on that, this is the more clear picture. So they have before the IPv6 plan, they have only IPv4, and the plan was like physics building and some block, chemistry building, admin building, and VLAN was like this is like flat plan. So there was no IPv4 only. There was actually IPv4 only address plans. Then as the Wi-Fi, they use a standalone Wi-Fi routers. There's no DHCP for wire user. Then after the planning, what we did is we just remove all their plans, and we suggest them to go not using the physics building, chemistry, any building wise. We suggest them to go for service wise. So after the plan, here is the picture. We suggest them using the wire user, the plan first, and then other consecutive IPv6 address planning considerations that we showed before. So during migration, it's already also going on actually. The migration process is going on. It's not completed. So during migration, we face some challenges like for network connectivity and current network connectivities, we don't need to change anything because the upstreams are okay, they support IPv6. But there is some problem like we have some equipment in Jahangirnagar University that doesn't support IPv6. So we either have to upgrade the OS or replace the equipment with new one. So VLAN and IPv6 plan is done, and then we go for dual stack. Then starting from the core, we are moving towards the distribution and edge devices. And then each stage we have to we have to test whether it's working or not. So there is just the common challenges. I think everyone faced that. So we also face those challenges. Some recommendations like some may think like we have user space, better to take some of them and keep the rest spare. But my suggestion, and it's actually suggested by the University 360 experts, they suggest to play with the whole block. Don't keep anything like we'll use this later. Whatever you are reserving, reserve with a better plan. Okay. So each customers can assign /40 so that they can route it. There are some reference for you to read and go through during your spare times during this week. If you have any question, I think it's too long. So if you have any question, then I may try to answer. It's okay. Thank you. Thank you all.
Thank you all. Very small quick survey. How many of you are using IPv6 in your office? Come on. From Bangladesh. Only 1, 2, 3, 4, 5, 6, 7, 8 out of 120 people. Okay. How many are using IPv6 in your home without Donald? And without John? In Bangladesh. Okay, how many you are using IPv6 at your home outside of Bangladesh? Donald? Okay, 3, 4, 5. So nobody is using IPv6 in your home. Why? Okay, so thank you, Abdul, and it's pretty good presentation. We've got so many examples, so we can we can use those. Now our next presenter, who is from Cisco, and unluckily who couldn't join us. He is a half Bengali because he is from Kolkata. What I should say, he is an Indian working for a US company but living in Singapore. So many combinations. His name is Shantanu Gupta. He is how many degrees I don't know. He did his bachelor from Jadavpur University. He has a CCI. He has a CCNP. He has so many things. Now he is working in Cisco as a senior consulting engineer for some global service provider network, and he will be joining us with his Skype, and he has a video presentation for 30 minutes, I guess.
নমস্কার, প্রথমেই আপনাদের সবার কাছে সাহায্য করে ক্ষমা চেয়ে নেব। আমার ঢাকায় যাওয়ার কথা ছিল but due to some last minute challenges on the video, I actually couldn't make it physically. So my sincere apologies to everyone in the audience. And I promise that for the next video meeting, I will physically there for sure. Okay, so what I'm going to talk about today is all the challenges of layer 2 need-based architecture for the next generation BCE or network function virtualization type of deployments. Now, I know it's pretty sure that this might be a very advanced and little bit of evolved topic for many of you in the audience because I'm not sure in what stage of readiness the Bangladesh market is right now when it comes to network function virtualization. But I thought it might be very, very worthwhile to take a look and understand the challenges so that whenever some of you feel free to become ready for deploying some of these architectures like this, you can probably take the right decision, in your decision-making cycle. So what I will do in the context of this presentation today is that first give a very high level overview of what network function virtualization is all about. I'm not going to do that for a long time because I already did that at the last panel, which happened at Candy in the month of January. So feel free to take a look at that deck for more details. And then I'll briefly introduce that what is the current method of doing service delivery when it comes to managed CPE in a L3 VPN context. What are the perceived challenges or the real challenges in the architecture? And why the layer 2 need-based architecture was proposed as a potential solution. And after that, I quickly also show you that what is the layer 2 need is all about. And then we'll get into the real discussion of this session, which is that layer 2 need-based alternate proposal, which has been proposed as a solution to solve these problems that we have today, is that very clean? Do we have challenges there? And if we have challenges, what are the magnitude or type of those challenges? And finally, I'll show you the conclusion and my recommendation that how we should, try to evolve the architecture moving forward in the context of the problem that we have today. Okay, so with that, quickly getting into the first section, which is the introduction of network function virtualization. And again, in the same slide, saw my candidate, and there are a bunch of network functions that we deal with in every day in the SP network architecture landscape. This can be subdivided into multiple different pockets, can be access, can be different services, can be network appliances, which are delivering different subsystems and control functions, different data functions, different gateway functions. Depending on what type of network functions they are in a SP network architecture landscape, what kind of data plane throughput they need to satisfy the role, what kind of controls and scalers that they need to satisfy the role. The appeal of virtualization for different functions comes at different levels. So some functions like a firewall or load balancer or a DPI or a control plane functions like a router setter typically early or low hanging target for virtualization where things like core routing or carrier Ethernet for data center switches may not be a good target for virtualization because of their high scale and throughput need on the data side. But in general, what is the virtualization of network functions as a concept altogether, or network function virtualization, or it is called as NFV in the industry today? So today, network functions runs within hardware, where the hardware, the integrated software, the operating system, and the pieces which are delivering the network functions are very tightly integrated together. A lot of people call them like a vertically integrated stack between hardware, software, and the associated applications. The virtualization of network function is trying to advocate on evolution, where you decouple the software from the hardware, and then pour the software along with the app to run as a VM or a container on top of a x86 standard server to deliver the same network function. So why we should do that? Because the moment you make it a virtual machine or a container which is running on standard x86 server, there is a promise that it can help reduce the cost, number one. And obviously, a much bigger motivation is that moment this is virtualized, I can turn this off, I can move this across, and I can turn this down with a policy, right? So I can turn off a firewall when I need a firewall. I can scale up that firewall when I need to scale this up, and actually deliver more performance or so forth. I can change that firewall with a bunch of other functions to deliver a particular set of services. And if I don't need it, I can turn it down and speed up my server resources for running something else. So that's the prime or the main promise of network function virtualization towards solving a big problem in the SP industry, which is called agility. Or in other words, today we take months and years to create new services, and then we have a huge promise to reduce the cycle down to maybe a few minutes or maybe a couple of hours. So how that can happen? That's exactly where concepts like NFV, software-defined networking, and orchestration has to come together and work in hand. So let's take a quick example of a very high-level snapshot where we are trying to build a service chain. Where in the service chain, I want to apply these services in line as the traffic passes through a customer VPN towards the internet. And what those three services are, as you can see on the slide over the top. I have a firewall, before the firewall I have a NAT, and after the firewall I have a DPAC administration. So these are the three services which are being applied to each and every traffic which is going from left to right, and also for the return traffic which is coming from right to left. So how this might happen in an orchestrated environment which is leveraging both NFV and SDN. So first of all, orchestration system will spin up this VMs, either in the same server or on different servers. Again, you can define them through your policies. Then the SDN system will be able to programmatically clump all of this together to build a service chain. Again, who defines this with topology? It's something new or the end user who defines the topology. And then finally, you push the configurations within those NAT firewall or DPI VM to make them like a NAT or a firewall, where you actually push in policies or rules like ACL, for example, that forbid web traffic but block FTP traffic or what have you, right? The last before the least is then the service chain needs to be stitched on both sides on the internet and also on the L3 VPN. Maybe this is where you're stitching the service chain into the respective VR on your network. And then finally, once the system is up and running, your continuously performance assurance analytics and if required the OM toolkits. You're applying the toolkits to ensure that you're able to deliver the required SLA and you're about to assure that the services that you're delivering is meeting all the performance and SLA requirements. Now, with that as a background, let's try to quickly look at how, in today's context, managed CPE with MPLS, L3, VPNs are delivered. And I'm sure all of you know this picture very, very well. When we have an MPLS core that has provided edge routers and key routers, core routers. Typically, they're connected to the C routers, which are located at the branch either by direct connectivity or using a shared Ethernet or backhaul network on both sides. And between the CD and the P, we run some form of IGP or EBGP or static routing protocol, which is often called as the PAC routing. And between CD to PE, we run MTBGP, multi-protocol BGP, either using direct P to PE mesh, or we can use a BGP router vector for doing that. Typically, most of the time you see that we use a router vector. Now, the Z routers typically, which get deployed in these type of networks are, most of the time you see this coil parts of the router being deployed. They are very feature rich, have 30 years of long Cisco innovation. But these are different sets of thoughts which are coming into the market for quite some time that this architecture is not really very flexible. And there are certain issues which are very, very genuine, there are certain issues which are foreseen, but let's take a look at what two issues. So obviously, most of the time, we see that this framework lacks automation. Or in other words, the CPE provision and the servicing of CPE often requires truck roll. And truck roll means that if you're an operator, you need to send an engineer down to your customer's premises to either turn on the CPE or to troubleshoot the CPE if something has gone wrong. Now that leads to high OpEx because every time they involve sending an engineer to and fro towards the customer premises. The other issue is the amount of feature sets that many of the times we run on the CPE, which is running on the premises of customer, makes the solution a little bit complex to operate. Because more and more features we run on customer's branch, which we need to manage remotely, which is not in my direct control in my own premises. So that gives a little bit of sense of more complex nature of operation. And that's some of the problems that many of our operators are facing today. The bigger problem is the service delivery in this mechanism is not really agile. It lacks automation. And the service startup and changes take a lot of time. So, I mean, if I need to add a firewall service in this, in this particular ATM, it might require quite a bit of time because adding a firewall in this whole service framework might not be that simple because I have to go read a lot of property management, I have to actually insert the firewall in the data path and whatnot. The other thing that we also hear a lot from many customers are the on-site CVs are often quite expensive and they're again vertically integrated between hardware, software, and applications, so which actually at times doesn't give a very common sense of openness, where it is very difficult to bring in third-party applications or third-party software to deliver new services on top of our own platform. So that's the other which is quite well heard of that we hear from multiple customers across the world. Now, the industry is definitely expecting something which is more, of course, which is more agile, fully automated, so that we can start a service and we can modify a service pretty much on the fly. And very importantly, it should be also able to address different market segments like large enterprise, medium enterprise, small medium business. Let's do the architecture framework where we have CPUs of different price points, activities of different price points. And service delivery framework, which doesn't take much time to talk about new service, most likely it is sort of self-service mechanism. So that we can deliver all these services in a very flexible and agile way to the market. So that's exactly where the virtual CE architecture discussion came up in the industry with a layer to NIC on the premises for business needs. And this discussion is something which is not new. We started almost like 2 years back and maybe 2.5 years back. I've been actually doing this pretty much from my earlier days when I started doing NSBM, already almost 3 years from me now. I've been doing this and I've been hearing this from pretty much from day one. Okay, now to move forward, let's try to take a look at what is layer to need in the okay. Some of you guys might be already familiar with it, but I thought it might be a good idea to define what is a layer to need for the sake of the audience, just to ensure that we are on the same page before we move any further in the presentation. So layer 2 NIC is nothing but a layer 2 network interface device. So that's what the NIC stands for. So I added to the platform. And what does it do? Essentially, the NIC is nothing but the carrier Ethernet operator's demarcation point, right? So think of you as a carrier Ethernet operator, and you are trying to provide a connectivity to a customer's branch. How do you provide the connectivity? Do you just go and drop a Ethernet cable and expect the customer to connect the Ethernet cable on any of the switches that they have? Well, that can be done. But the problem in the approach is, if you do not put a small device which is under your control, then you do not really have a ability of performing end-to-end SLA and performance management. If you do end-to-end SLA management, end-to-end performance management, then it requires certain feature sets on the device which terminates the Ethernet cable of the customer branch, right? If you are to do, for example, remote service activation or remote loopback or troubleshooting or what have you, there are so many different use cases which makes us NIC to be a requirement. And that's what most of the operator does. They don't just drop the cable. Along with the cable, they also put a switch, which is the NIC, and they terminate the Ethernet cable on top of the switch, and that becomes the customer's and the NC demarcation point. This is usually managed by the operator, which has the user facing port, which is the UNI. That's where the user comes and the connectivity happens to the branch. And of course, they have the NNI code where they go back and access the carrier Ethernet network, right? Typically, it's a 4 to 6 port or 2 to 6 port Ethernet switch that might have a 3 dB or 10 dB ports. And on top of that, it needs to have certain advanced capabilities, especially for doing all those management, service activation and troubleshooting. And they typically are in third OS, like CSM Y2031 for and some fault management. Service activation is protocols like Y.16, 1564 and time support because many of the times these needs are dropped at the places where and it has to perform over. So that's a very simple and quick way to define what is a layer to need all about. Okay. Now with that, let's take a look at what was this L2 NIC plus VCP architecture that was proposed to solve these challenges that we described a couple of slides back in the traditional model. Now this picture is showing the traditional model where I have the service edge here, which is a PE, and this is a performing MPLS L3 VPN services. So this is the L3 VPN PE. I have a customer frame, and in the customer frame, I have a layer to NIC, which was dropped by the carrier Ethernet operator to target the carrier Ethernet circuit, and behind the L2 NIC, there was a L3 CP, which was actually providing the L3 VPN function, and this CP was performing PEC routing across the carrier network towards this L3 VPN, and that's where the services were being delivered. The ordinary proposal of the electronic plus VCP architecture was that remove this CP inputs from the branch and make the branch only to run with just some layer to NIC only. But guess what? I need a routing function somewhere so that the routing function has to run the routing on behalf of this customer branch. So the proposal was, so let's use the physical network from the customer branch and spin this up as a VM in an NFV data center somewhere in the SP hosted premises running as a virtual CPE. And this virtual CPE, of course, is CPE function which is virtualized and it is running all complex feature sets like routing, hierarchical queues, NAT, firewall, what have you, right? Like typically what all we see in a typical Cisco router provided the VCP also has the similar capability or available feature sets part of it. So that was our proposal. One thing, remove the LCCP from on-prem and just make it part with simple network and spin the CPE as a virtual function in the SP's premises, maybe on an data center, as a virtual function and run the routing. And there we have to make sure that the L2 traffic is backward from the customer branch towards the VCP or the carrier Ethernet network. And from the VCP to the PE, it will be the standard PEC route. So think of it that that physical order has not been now being shifted to this place here and made it virtual. That's what makes it the requirement of backhauling the layer to traffic all the way towards this virtual CPE because the default gateway for this branch is actually now residing here on the VCP, right? Okay, now why this alternate architecture looked promising? So this was a traditional model where we have physical electricity on branch and on NIC, a traditional way of running the LCD. But with the L2 NIC plus VCP architecture, the physical CPU was no longer required as promised, and this could have been handled with a virtual CPU. So the promise of the attractiveness here was that we have a chance here to simplify the customer premise